Welcome to this explainer. Today we're diving straight into one of the absolute wildest journeys in all of science. We're going from the unbelievably tiny space inside an atomic nucleus all the way out to the immense star-powering forces of nuclear physics. We're going to explore how the invisible building blocks of our entire universe have enough locked-up energy to power whole cities, or, if left uncontrolled, cause massive destruction. So, let's kick things off by imagining a completely overpacked suitcase right at the breaking point. You know that exact feeling, right? You've stuffed so much in there that the zippers are literally straining, and eventually, the structural integrity just fails. It has to burst open to relieve all that intense internal pressure. Well, in the atomic world, when a heavy nucleus holds too much energy or has an imbalance of particles, it behaves a whole lot like that overstuffed suitcase. When that atomic suitcase finally pops open, that's what we call radioactivity. Now, the source material emphasizes two absolutely crucial words here: spontaneous and random. This decay is a totally spontaneous phenomenon. It happens purely within the nucleus itself, meaning it is completely unaffected by outside physical pressures, temperature shifts, or chemical reactions. You can't freeze an atom, heat it up, or chemically react it to stop or start this process. No way. It's simply the nucleus trying to find stability by emitting alpha, beta, or gamma radiations. Here is our roadmap for today. First, we'll look inside the atomic nucleus, then unlock the discovery of radioactivity. Third, we'll break down alpha, beta, and gamma radiation, move on to fission and fusion, and finally look at nuclear power as a double-edged sword. All right, section 1, inside the atomic nucleus. To really grasp this immense power, we first have to zoom way in, specifically on the order of 10 to the negative 15 meters small. That's the unimaginably tiny domain right inside the nucleus, where positively charged protons and neutral neutrons hang out. Let's break down how these atoms actually vary. We have isotopes, which have the same atomic number, so the same number of protons but a different number of neutrons. Then you've got isobars, which share the same total mass number but differ in protons. And finally, isotones, with different proton counts but the exact same number of neutrons. It's super important to understand these variations because unstable isotopes, atoms with an excess of neutrons, are exactly what drive the radioactive decay we see in nature. For example, the unstable isotope carbon-14, that's the literal mechanism we use for carbon dating ancient artifacts. Moving right along to section 2, unlocking radioactivity. How did early physicists move past Henry Becquerel's 1896 discovery, where he accidentally left uranium salts on a photographic plate, and actually visualize these invisible forces? Rutherford's classic 1903 experiment brilliantly illustrates this. By placing a radioactive substance inside a lead box with just a narrow opening, he directed the emitted radiations through a strong magnetic field. The beam actually splits into 3 distinct paths. The positively charged alpha particles bend to the left, the negatively charged beta particles bend sharply to the right, and the uncharged gamma radiations shoot straight through without deviating at all. This simple but absolute genius setup proved the existence of 3 very different types of radioactive emissions. So, section 3, alpha, beta, and gamma. What exactly are these 3 separate beams that Rutherford's magnetic field revealed? There are some really stark contrasts here. Alpha particles are basically heavy helium nuclei, 2 protons and 2 neutrons. Because they're heavy and carry a double positive charge, they pack a massive ionizing punch, knocking electrons right off nearby atoms. But the trade-off? Their penetrating power is incredibly low. A single sheet of paper will stop them. Beta particles are fast-moving electrons, and you'd need a few millimeters of aluminum to block those. On the total opposite end of the spectrum, we have gamma rays. These aren't even particles. They're highly energetic electromagnetic waves traveling at the literal speed of light. They have low ionizing power but require thick blocks of lead or meters of concrete to stop their intense penetrating power. Let's see how this all builds into an actual nuclear transformation. When an unstable parent nucleus, like uranium-238, undergoes alpha decay, it ejects that heavy alpha particle. Because it loses 2 protons and 2 neutrons, its atomic number drops by 2, and its mass number drops by 4. The crazy part here is the transmutation. Emitting just one simple alpha particle completely changes the element's fundamental identity, from uranium into thorium. All right, section 4, fission and fusion. We are scaling things up now. We're moving from the single, spontaneous atomic decays of natural radioactivity to the deliberate, massive energy releases we use to power our modern world.
To put the sheer scale of this energy into perspective, we have to talk about Einstein's famous mass-energy equivalence, E equals mc squared. In nuclear reactions, a tiny, tiny amount of mass is lost and directly converted into energy. Losing just one atomic mass unit releases a staggering 931 mega-electron volts of energy. To give you some context, a standard chemical reaction, like burning a piece of coal, releases energy on the order of just a few single electron volts. That means a tiny nuclear mass lost yields roughly 1,000,000 times more energy than a normal chemical reaction. 1,000,000 times.
This is where we see the mechanics of nuclear fission in action. Imagine a heavy uranium-235 nucleus getting hit by a slow-moving neutron. The nucleus absorbs it, gets incredibly unstable, and instantly splits into two lighter fragments, like barium and krypton. But here's the kicker. It also releases 3 more free neutrons and roughly 190 MeV of tremendous energy. Those 3 newly freed neutrons can then go on to split 3 more uranium nuclei, triggering this explosive, cascading chain reaction. If we control it in a reactor, we get steady electricity. Uncontrolled, that's the devastating basis of a nuclear weapon. Now, while fission is all about splitting heavy atoms here on Earth, which makes power but leaves behind radioactive waste, fusion does the exact opposite. Nuclear fusion is combining 2 light nuclei, like isotopes of hydrogen, to form a heavier helium nucleus. But trying to shove 2 positively charged nuclei together means fighting massive electrostatic repulsion. That's why fusion requires unbelievable heat and pressure. We're talking roughly 10 million Kelvin. This is the exact thermonuclear reaction happening constantly inside our sun and the stars, pumping out life-sustaining energy with 0 harmful radioactive waste. We just haven't quite figured out how to efficiently sustain that plasma reaction here on Earth yet. Section 5. A double-edged sword. Understanding all this staggering physics brings us to a profound crossroads. Nuclear energy is the ultimate double-edged sword, offering both incredible modern miracles and immense biological hazards. Think about this incredible duality. The exact same highly penetrating gamma radiation that can easily destroy the DNA and RNA of living cells, causing severe, multi-generational genetic mutations or acute biological damage, is the very tool we meticulously harness in medicine. We literally use controlled radioisotopes in radiotherapy to selectively kill malignant brain tumors, cure forms of leukemia, and safely sterilize surgical tools. It all comes down to how we direct and control the exposure. Because background and emitted radiation are always present, managing them demands our ultimate respect. The safety precautions are intense. Medical personnel have to wear special lead-lined aprons and film badges just to monitor their exposure. On an industrial scale, we're talking about housing nuclear reactors in massive, airtight buildings made of incredibly strong concrete designed to withstand earthquakes. And honestly, the most daunting part is the waste, burying spent radioactive fuel rods in thick casks sealed deep within isolated underground mines so they can slowly decay over millennia. So, as we wrap up this explainer, consider this stark reality. Through human ingenuity, we have literally unlocked the fundamental power of the universe, the very fire that lights the stars. And we've brought it down to Earth. We hold this astonishing capability to power civilizations and cure diseases right in our hands. But given the scale of safety required, ask yourself, are we truly prepared for the permanent, thousands of years long responsibility that managing its radioactive waste demands? Keep asking those big questions and keep exploring the science that shapes our universe.